My presentation focuses on a subnational age structure modeling approach of malaria transmission and burden. Some issues. I'm going to present the background and afterwards the model framework, some application of the model on 4 African countries and conclusion. So malaria transmission vary significantly across administrative units, even within a same country. And therefore, national estimates mask this as strong variability and age-specific variation. Also, most impact of control strategies against malaria depend on the local transmission intensity, depend also on the age cohort, and also the different control strategies implemented and the immunity of people. And nowadays, policy decisions require information on malaria dynamic at administrative units, not at national level. And about age structure, we all know that children under 5 are the most vulnerable to malaria and bear the highest malaria burden. Why? Because there is a gradual immunity builds up, and the implication is that subnational model is very, let's say, important to implement efficiently control strategies, and also age structure model help in efficiently evaluate some interventions like vaccine, which targets under 5 children, first 2 years children, and also seasonal chemoprevention, targeting under 5 children. So the subnational model that we built is an extension of a recently developed national model of malaria transmission, accounting for vaccine and non-vaccine intervention. So you can see on the screen the flowchart that is considered. So for each of the age cohorts from 1 month to 100 years, this flowchart was considered, and we can notice 4 different emphasis compartments: asymptomatic individual, uncomplicated malaria, severe malaria, and admission to hospital from severe malaria. And we distinguish between in community case fatality ratio and hospital case fatality ratio. So the ordinary differential equation focusing on the temporal dynamic and the aging of individual. Now, moving from this national level model to a subnational model require some parameterization techniques. So here I distinguish between parameters which vary according to administrative units and parameter uh, which can be considered as fees at the country level values. So about the spatial heterogeneity parameters, we have the entomological inoculation rates, which vary considerably across administrative units, and the proportion of emphasis mosquito, and of course, the death rate for severe cases in community death rate and hospital death rates. So these parameters vary according to administrative unit within a country. And about the non-spatial heterogeneity, we have, for example, a proportion of clinical cases that progress to severe cases, immunity parameters, probability of developing symptoms after malaria infection, and the recovery rates of asymptomatic individuals. Most of these parameters depend on the immunity of individuals. And how we derive the subnational entomological inoculation rates. We use an approach similar to that of Smith and collaborator 2005, and we derive the subnational entomological inoculation rate considering local malaria prevalence. And we link this with the country level entomological inoculation rates. So using expression 2 and 3. And in this expression, what is interesting is the parameter B, that is the degree of a spatial heterogeneity in the distribution of entomological inoculation rates across administrative units within a country. We also consider the proportion of emphasis mosquito. The proportion of emphasis mosquito is used to derive the biting rate from the entomological inoculation rates. And this proportion of emphasis mosquito varies according to the administrative units. Due to the variation of local malaria prevalence. So we consider the expression in 4 where this parameter is computed per administrative unit considering the population weight, W, and also considering the prevalence. And what is also interesting here is the parameter gamma that represents the degree of spatial heterogeneity in the distribution of this proportion of emphasis mosquito as for the entomological inoculation rates. Now, how did we approximate the subnational death rate and death rate for severe cases? We start from the case fatality rates, considering the observed death, malaria death, and observed clinical cases in each administrative unit. We consider the case fatality ratio, overall case fatality ratio for severe cases. That is the sum of all deaths over the sum of all clinical cases. But we know that clinical cases do not lead to death, malaria death, only severe cases. So we need the proportion of clinical cases that progress to severe cases. And this parameter uh, is considered in the denominator to avoid having zero at the denominator. Sorry. Um, okay, so to avoid having zero in the denominator, community treated cases. So we derive from the overall severe cases, the community-treated cases and hospital-treated cases, considering the probability of being admitted to hospital. So from this probability, we can derive the hospital case fatality rate and the community case fatality rate that we suppose are time the hospital case fatality rate. So from this two case fatality rates, since there are probability and we want a death rate in the ordinary differential equation, we use the exponential survival model theory to derive the death rate, hospital death rate, and in community death rates. And afterwards, we also considered non-vaccine intervention, the three main non-vaccine intervention, so long-lasting insecticide nets, and indoor residual spray and seasonal chemoprevention. So for the insecticide net, we consider that the net reduced the biting rate with a used lifetime that is T, 3 years. So after 3 years, the net is renewed. That's the reason why we consider modulo here. And we also consider that since the net is an insecticide net, so the net also increased mortality rate. So using expression 8, and considering the indoor residual spray, we consider that the spray also increased the mortality rate. So we use a combined effect of the insecticide net and the indoor residual spray to have an increase in the mortality rate of mosquito, considering that there is an exponential decay of the efficiency of indoor residual spray once used. Regarding the seasonal chemoprevention, we consider that it reduces the age-time dependent force of infection for children from 3 months to 59 months. And we consider different rounds of the application of this intervention, and with an efficacy that decreases in time using an exponential decay function. So illustrated by expression 9. We also consider immunity in the model because immunity plays a significant role in malaria incidence and death. So we consider maternal immunity because some studies show that immunity is transferred to babies from mother at the very early age, before 6 months. So, and this immunity decreases, and we consider, following malaria literature, we consider an exponential decay of the maternal immunity. And we combine, of course, this maternal immunity with the natural acquired immunity. And this is illustrated by expression 10, 11, and 12 that also accounted for the time-dependent entomological inoculation rate and the life expectancy. And from the expression of the immunity and following the excellent work by Felipe and collaborators, we show that immunity acts at the level of the probability of developing symptom, at the level of the recovery of asymptomatic individual, and the warning rate of acquired immunity. So we express the probability of developing symptom in the function of immunity using expression 13. And regarding the recovery rate of asymptomatic individual, still following Felipe and collaborators with the epidemiological studies, we express the recovery rate of asymptomatic individual as a nonlinear function of the immunity, expression 14. And the warning rate of acquired immunity is still following Felipe and collaborator, which show a clear relationship between warning rate and acquired immunity. We use the expression 15. So we updated the previously used expression in the recently published national level model, considering here the immunity instead of the age-time dependent force of infection. And we also consider the rainfall seasonality, because rainfall impacts the birth rates of mosquitoes. So we express the recruitment rates of mosquito in the function of the peak of rainfall in a year, and also the lag effect, because it's not when the rainfall, when we have high rainfall value that the recruitment rate increases or become the highest. It requires a time. That's the lag effect, generally 1 month. So we also account for the seasonal function of the rainfall, and now the calibration of the model. So to calibrate this subnational model, we start with the country level fitting. So what we notice is that there is a great interannual variability in malaria cases and death. And this can be only explained by an interannual variation of the prevalence. So instead of considering a constant entomological inoculation rate in the model, we consider a time varying entomological inoculation rate, considering the interannual malaria prevalence. And we can also see here that national B is the degree of heterogeneity in the distribution of the prevalence, considering the historical periods. And we also consider a time-varying death rate. So linking death rate to time-varying case fatality ratio and using a country-level proportion of clinical cases that progress to severe cases. And when we finish with the country-level fitting, we focus now on the subnational fitting, where we compute the subnational entomological inoculation rate, malaria mortality, considering the proportion of severe clinical cases that progress to severe cases for each admin 1 unit. And with this, we consider that all the other parameters are constant across admin 1 unit within a country, and this at the country level estimate from the country level model. And then the transmission model at the subnational level was then run independently for each admin 1 unit. Now, the big issue here is that aggregating simulated subnational cases does not yield exactly the country level estimates. Why? Because of the non-linear characteristic of malaria dynamic. So to enforce the subnational cases and death, so that when we sum them, it yields exactly the country level estimate. We use a normalization process where we compute a ratio, RC and RD, RC for malaria cases, RD for malaria death. And RC is the country level estimate, so not reported, country level estimate over the sum of all admin 1 units. And same thing as for death. And then from this value, we can now rescale the malaria cases and death at a national level, subnational level. So we rescale the malaria cases at subnational level and malaria death. And since we can do this only for the historical period from 2000 to 2024, we use the trends of this ratio to model the value of the ratio of the two ratio in the function of time, using these two expressions where we have lambda C and lambda D, which indicate the speed of change in the ratio. So we estimate these two parameters using historical values. And we calibrate the model computing not only parameter B, but also parameter gamma. So parameter B is the degree of spatial heterogeneity in the entomological inoculation rate, in the distribution of entomological inoculation rate. We also consider parameter gamma, which is the degree of spatial heterogeneity in the proportion of emphasis mosquito. So we calibrate these two parameters using the root mean square of observed and estimated and rescaled malaria cases and death. Consider a weight to have same magnitude for cases and death. So by minimizing the root mean square, we estimated B and gamma. Now, application of this new subnational model. We consider 4 countries, high transmission countries like Benin and Burkina Faso, and low transmission country, Ethiopia and Somalia. We use data on malaria burden. We download the data from the Malaria Atlas project site web, the website there. And we use MATLAB to code the model. And the model, the codes are available in my GitHub session, but not yet public because I'm on the way to submit the manuscript. It's a very new model. So, at a country level, we can notice here a good fit of the model. And at the subnational model, so the parameter estimated, table of the parameter estimated, where we have the country level entomological inoculation rate, the proportion of clinical cases that progress to severe malaria at a national level, immunity parameters, and also the root mean square for the country level model and for the subnational model. And we show here the fits of the model comparing reported and estimated malaria cases at the subnational level. So the 12 administrative units in Benin, and also the same as for Burkina Faso, for Ethiopia, and for Somalia. So we can see overall good fit of the subnational model. And here we show the case fatality rates of malaria at the subnational level for Benin and Burkina Faso, high transmission countries. And we can see here that there is a great variability in the entomological inoculation rate across the admin 1 units. So from 90 to 130 regarding the EIR, and for the case fatality rate, also great variability. What is interesting to notice here is that there is no link between the variation of the entomological inoculation rate and the one linked to the case fatality rate. And this is very interesting. It means that local transmission cannot explain alone the case fatality rate. And there are other factors like case management and also immunity parameters, and most importantly, control strategies implemented, which vary from one admin one to another. And we have the same trend here for Burkina Faso, where we see a great variability across admin 1 unit. And the variation are not similar. And for the low transmission countries, we notice first that the entomological inoculation rate, estimated entomological inoculation rates, are very lower than the high transmission in the high transmission country, from 8 to 30, less than 30. And same thing as for the case fatality rate, that is relatively low in the low transmission country. And we can see a great variability in entomological inoculation rate and case fatality rate in Somalia, greater variability compared with Ethiopia. And we also consider projection over 2050 of the cases, malaria cases, and death, distinguish between the whole population and under 5 individuals, under 5 children. And we can see here a great variability across admin 1 unit, relatively same magnitude of malaria cases for the whole population and the under 5 children. So we notice that regarding the death, we notice that under 5 children bear the highest malaria death in red. But in Burkina Faso, we can see that we have the same magnitude for the whole population and the under 5 children. And the variation is not so important across administrative unit compared with Benin. For the death, what we notice is that higher death in under 5 children, but from 2020, 2023, we have almost the same value for malaria death for the whole population and under 5 children. And this is probably linked to the control strategy implemented in the country. For the low transmission country, Ethiopia, we also notice great variability across admin 1 unit for case and death, and similar malaria case and death for the whole population and under 5 children, and also similar trends for Somalia. Now, a key insight from this study, we can notice that malaria burden is highly heterogeneous within countries. And also, case fatality rate does not follow transmission intensity. We have some high transmission setting with lower case fatality rates and low transmission setting with high case fatality rates. And for policy relevance, we can say that national estimates are very insufficient for an efficient malaria control in African countries. So we need a geographically targeted intervention, focusing on administrative units and focusing on the age-specific pattern. And this new model is very suitable to evaluate the vaccine impact. Why? Because vaccine targets target under 1, let's say under 2 children. So the first dose at 9 months and the booster dose 1 year after. And the model also a low long-term projection to, let's say, evaluate the dynamic of malaria over 2050, even 2100. Thank you very much for your attention.